uh, to give the access to Dr. Noor.
Assalamu alaikum. Good afternoon, all by Egypt time.
Yes,
Let me first ask if you are listening my voice clearly.
yes, Professor Noor, I am listening you clearly. And before you start, I will give a short introduction about you. Then you can start. Still, there is
Okay,
5 minutes are there. You can wait, sir. Mm,
my pleasure, Professor. Okay.
mm. And good evening to the host coordinator, Dr. Shankar Saigalji, and good evening to our expert. So, today is the second day. We are going to start our session, and we have with us Professor Noor Mohammed. He is an assistant professor at Mechanical Engineering Department at Beneha Faculty of Engineering, Beneha University, Egypt. He did its he did his PhD from Egypt, Japan, University of Science and Technology. His area of research is design and development of alloy using a soft computing method such as machine learning. He has published numerous number of paper in a journals, reputed journal. So his talk is going to be very interesting for the participants interested in machine learning, how to design an alloy for a particular application. The talk of the Dr. Noor, Professor Noor, will be focused on designing the biomaterial using a soft computing method. So, participants, as already Professor Shankar Sekhar has informed you that 80% of attendance is compulsory, and you have to clear the test after the finishing of this course. So, I welcome you all the part again. And one quote I want to say over here is that as the Dalai Lama says that when you talk, you are only repeating what you know. But if you listen, you are learning something new. So you participant very lucky that you are listening expert lecture from the expert uh, professors from all over the world. So now I request Professor Noor to start its lecture. Please, over to Dr. Noor.
Okay, thank you very much, Professor Silva. And I'd like to thank you first for this valuable invitation for this event. And I hope that the lecture adds something new to all of our audience. Let me share my presentation first. Is the slide clear now? You can see the slide and it is moving.
Yes, it is visible. Mm.
Okay. If you face any disturbance during the lecture, like stopping of the
Okay.
slides or interruption in internet connection, just let me know. Okay.
Mm. Yes, I will inform you, sir.
Okay. Welcome to next generation of biomaterials, clinical translation through machine learning. And today's talk about metallic implant design using machine learning. And I am Dr. Noor Mahmoud Dabbah from Banha Faculty of Engineering, Banha University in Egypt. I will skip the introduction as thanks for Professor Seto for his introduction. And I will go for the content of this presentation. I will speak first about material evaluation, metal implants, orthopedic implant design criteria, overview of AI, machine learning, and finally, which is the most important about our talk, is a case study. We will check two of my case study about designing a metal implant defined or classified as high entropy alloy implant material using AI. But if you look for the content, you will find some topics or some point which may be deviated away from the point. This is you may think like this, but actually the first point regarding the machine learning or AI designing your alloy or your material, you should know its pillars first or the criteria for the design first. This is important to know how you will utilize your machine learning and AI techniques in your design. If we look for the evaluation of material over history, we can find that in the first start of human creation, humans start to use everything useful about around him or surrounding to him, like wood, pottery, rocks, and so on. The matter evolved uh, somehow, and some processing have occurred to material, and we have some pottery, which was manufactured by Chinese and old civilization in the Middle Age. And finally, which is the most important, is the discovery of metals and alloys. Start first by borons for making states and alloy or iron alloys, which has been used in manufacturing of weapons. And actually, alloys has evoked or started the evaluation in material science and engineering, especially in metal implantations. As you know, human body, we can find a lot of application of metal implants inside human body, like dental implantations or stents that are being used in artery of heart. Also for supporting fractures inside the bone or scaffolding for healing the skin. Overall, the body, we can find different alloys that are widely used, like stainless steel, titanium alloys, cobalt, chrome, molybdenum, also titanium 6, aluminum 4, vanadium, which some of the most important alloys that are widely used in both industry and medical application. Also, we can focus on some, or we may find some alloys like biodegradable or degradable alloys like magnesium and zinc alloys. These all are alloys are widely used inside the human bone implantations, and we can find different categories of these alloys and pure metals are being used. So before we start to utilize the machine learning in our work, we should understand the basic first, and this should be applied for each type of materials. For our case, we are going to design implant. So we should understand first what are the design criteria to make an implant. Efficient implant. What are the main characteristics? Because not all alloys and pure metals can be widely used in metal implantation. Here are some of the most important characteristics that you should consider for your design. And actually, the design of implant is not only this rule is not only finished after you supply the chemical composition to the manufacturing. This is not the criteria. The criteria that you design for every step of this implant. For example, you design for the processing, you design for the long life durability, you design your implant for post implantation investigation. Many rules that the designer should consider, or he should consider this criteria while designing the implant. Let me start first by the biocompatibility. Now we have agreed that we should make an orthopedic implant, and actually this design criteria are focused. The design criteria is focused on orthopedic implant, because each type of implant or each type of biomedical alloy need different criteria in mechanical properties. For example, the stent needs high strain hardening, low, for example, low spring back. On the other hand, the orthopedic implantation needs low elastic modulus, high yield strength, and so on. So before you go for AI, you should know first what are the basics or what are the fundamentals that I should follow for making efficient design for the implant. First of all is the biocompatibility. You are dealing with the human body, which is very sensitive to foreign metals or foreign substance that will enter the human body. In this classification, you will find that some of elements are recommended or strongly recommended to be used inside the human body, where other can be accepted for a low concentration, and some other are that should be avoided. You cannot use it. For example, titanium, zirconium, niobium are strongly recommended to be used, okay, till we reach to the 10. We can accept some amount of aluminium, manganese, iron, and so on. And we should avoid elements like platinum, nickel, cobalt, chrome, vanadium. And you should consider or put or bear in your mind that some of biomedical alloy like titanium 64 or cobalt, chrome, molybdenum, or 316 stainless steel are all containing some of elements that is not be accepted for implantation. That's why we need development or a research and development in the field of biomedical alloys to replace the toxic element inside the base to invent new alloys. Coming to the mechanical properties, and we will speak about around 5 elements or 5 core elements. First of all, for orthopedic implant is a low elastic modulus. Yes,
Sorry to interrupt, Professor. I think your first slide is appearing. Are you sharing next slides, or it is
the
stuck
first slide
on
is
first?
following.
Uh, the slide is not moving forward.
Okay, let me check. I will stop sharing
Yes,
and I will
now it is okay.
share again. Make entire screen. Now it is moving.
Yes, yes, yes. Now it is.
Okay.
Yes,
Uh,
yes.
Now we will speak about the implant design criteria, starting from biocompatibility and for the mechanical properties. We were speaking about the stress shielding effect. Stress shielding effect, this phenomena comes when we put inside the human body, for example, the hip joint. This is made for or manufactured from stainless steel or titanium, pure titanium. All are above 100 gigapascal for elastic modulus, and considering that the human bone is around 30 to 40, from 10 to 30 gigapascals, so we have a difference in elastic modulus, and consequently load bearing will be transferred more to the implant itself rather than the bone, which means that the cells of the human bone will not be rebuilt again, and meaning that the metal implant shields the curing of the human bone, and we will face osteopenia. Osteopenia means that the bone cells will not be rebuilt again, and we will lose the implant. So we should consider the acceptance in the elastic modulus or near value of elastic modulus between human bone and metal implant. And this point is the most important point, that we should consult the artificial intelligence tool for designing our alloy, as we will see in the next case slide. Secondly, we should accept acceptable ductility and high yield strength. And this is very important characteristics for the metal implant, and you should consider this while you make a mechanical or a tensile testing for your alloy. You should avoid the fracture, the brittle fracture of the implant. We should accept the ductile metal that will obtain a high toughness. It means that it will absorb some of the impact energy. For example, if the patient is exposed to a severe accident, for example, and we should consider the design in this case also, we shouldn't have a brittle fracture. Why brittle fracture? Brittle fracture is a catastrophic one. If the implant is catastrophically broken inside the human bone, it will tear the surrounding tissue, and in the same time initiate a crack inside the human bone itself. So you should accept ductile element, and this will be reflected in the constituent phase inside the alloys. For example, we know that some intermetallics, if appeared in your alloy, that it will increase its brittleness, and it will not be acceptable to be an orthopedic implant. Also, for the ductility, we should consider also for the process of the alloy, because all metal implants need cold working and drawing and rolling, so it should show some plastic deformation, so it will make it easy for the processing for your implant. So you, as a designer, you think also for the processing and the manufacturing of the alloy, not only the life of the implant itself or the service life of the implant itself. Finally, is the fatigue strength. For example, the knee joint is exposed to cyclic loading while moving, going upstairs or downstairs. So you are exposed to cyclic loading. So you should consider high fatigue strength of the alloy. Finally is the hardness, and the hardness give us some indication about wear resistance of the implant. Making it high hardness with low elastic modulus means that our implant is or have a good wear resistance characteristics, and this is strongly required for metal implantation. Also, from the most or the some of important characteristics like effective metal implant or sorry for physical properties. By physical properties, I mean I am speaking about two characteristics: is the magnetic susceptibility and radio opacity. For all material we have around us, we have when we classify them in terms of magnetic properties, we have ferromagnetic materials, paramagnetic, and diamagnetic materials. So why we are speaking about the magnetic susceptibility? This property is very important for post-implantation investigation of the implant. The implant or the patient, when he goes for MRI investigation, he's exposed to a very high magnetic field, I think around 3 teslas or something like this. uh, if a ferromagnetic material which responds to the magnetic field are implanted, for example, if we assume that uh, the patient is have some implant made of pure iron, you can imagine what will happen to him while making this investigation. يعني a severe accident will happen to him by being sucked to inside the magnetic resonance and may lead to death of the patient. So you should avoid the ferromagnetic and you should characterize your alloy in terms of magnetic properties. However, paramagnetic or diamagnetic, the difference is just in the direction of the magnetic dipole of the material, and we can know from the vibrating sample magnetometer magnetization curve if the slope of the fitting of linear fitting of the magnetic curve have a slope lower than 1, it is diamagnetic, or higher than 1, it's para magnetic. Considering that our human bone or human tissue is a diamagnetic material, so going to diamagnetic material is better and is most preferable to avoid severe accidents that may cause by magnetic field of the MRI. Also, the magnetocaloric effect. And magnetocaloric effect means that when a magnetic field applied to a ferromagnetic material, it will heat up the implant. Considering also our body temperature is around 37 centigrade Celsius, so heating up the temperature more than 37 over 50 or 60 centigrade Celsius will will harm the surrounding tissue for the implant and losing the implant in some cases. Also, the expanding of the implant when heating, the expansion thermal coefficient of expansion for the metal is not like the metal like the human bone, and in this case he will press on the human bone, causing a severe pain of the implant. So you should consider the magnetic property. For the radio opacity, it means that how the material will respond to the X-ray. As you can find in this image here, the implant is opaque, means that you can investigate it clearly when you investigate the patient. So this point, as a designer, you think for the service life of the implant, how it will be investigated and how it will affect the human body during the medical investigation of this body. Finally, corrosion properties, we need a low corrosion rate, because low corrosion rate or high corrosion resistance means that we have a stable dimension of the implant and effective service life of the implant. Secondly, the released ion or the released debris that may be caused by low corrosion resistance may cause inflammation for the human body, as we can find in this image here. Also, the passivation behavior and the composition of the passive layer is very important, because this is the first layer that is more connected to the human tissue, and the cell being at make its adhesion to the passive layer, and the proliferation is caused or is occurring on this passivation layer. Consequently, the characterization of the passive layer is important, considering some of titanium alloy may passivate after 1 hour. يعني just finishing the surgery, the passive layer will be formed, and cell adhesion and proliferation will happen after 1 hour after the surgery. So these are we can consider summing up the and considering of effective implant design. we may face toxicity or inflammation if we didn't consider corrosion resistance or fracture of the bone or pull out of the implant when we didn't consider the stress shielding effect. Now I think we have sum up some of the uh, we have sum up the design criteria for orthopedic implantation, and you have bared in our mind what property we should consult the machine learning and what are the criteria we should consider, what is the most important, and so on. This is very important to apply the AI and machine learning in our design. Let's make a fast overview about machine learning. The definition or the word itself, artificial intelligence, appeared in the 15th. And in simple words, artificial intelligence means that makes that making the machines behave smartly or respond to its surrounding. So this is the main definition of artificial intelligence. Going for more advancement, we have found the machine learning, and the machine learning appeared when the algorithms or the mathematical algorithms for regression and for classification has appeared. Going for most advanced is a deep learning, and in this case, we are imitating the human brain, and the human brain means that it can respond effectively to the surrounding and datasets. These are the category for supervised machine learning. You have a labeled dataset, and labeled dataset means that you know the classes of dataset, and the algorithm can classify for you different data. You can go for regression. You have, for example, we are speaking about the elastic modulus, and we have a chemical composition or input dataset. So you can make a regression pattern, and you can predict what the probability will be when the chemical composition will be X, Y, and Z, and so on. But if you have no labeling in your data are randomly have some properties, so the algorithm itself will learn from this data and make a clustering. He will classify the data for you based on the pattern exist. Finally, the reinforcement learning. This algorithm is learning from the environment itself and can take action from the surrounding environment. We can find many applications of machine learning around us. You can find it in social media or face recognition in your smartphone, also speech recognition and healthcare also. Many applications you can use the machine learning in it. What is important for us is a material science. As a metallurgist, what or how can I get a beneficial or get the benefit of machine learning in my design? The most direct is the property prediction. As we have stated previously, you have a chemical composition with a corresponding elastic modulus. So you can predict the elastic modulus based on the chemical composition. You can discover new materials. New materials can be discovered if you find certain property you need, and you can reverse the process to get the chemical composition, physical property, or a reaction condition for the chemicals, and process optimization. For example, and this is exists in the literature. You can optimize the processing, forging processing or treatment processing. This also could be accomplished using machine learning. So I think starting from 2010, machine learning should be incubated to all study of material science, because it fastens the process and make it more accurate and give reasonable results. So if you allow me for a 1 minute break, and we will go for the case study designing for high entropy alloy, and we will see in this part how two cases actually how we will use the machine learning or AI in studying or designing our alloy for orthopedic implantation. So I execute or excuse for Professor Sito 1 minute rest,
Yes,
then I can.
why not? Yeah,
Also, if you
please.
want to ask any questions, if you need, I'm ready.
you can raise your hand. We can unmute you for the questions.
So if there is no question, I can continue now.
Yes, the
Yes.
participants have decided to ask question
Okay.
after a session. Uh,
Okay, no problem.
hmm. If you have,
Now come.
sorry to interrupt. Sorry to interrupt. If you have, dear participants, if you want some clarification in between the lecture, you can raise the hand. We can unmute and interact with the Professor Noor. Okay, thank you.
You continue.
Yes, please continue your lecture.
Okay. So now after we have an idea about AI, machine learning, and the implant design criteria, we are ready now for studying our case study here for designing high entropy alloy implant materials. If you remember the first slides, in the first slides we using most alloys are traditional alloys like titanium alloys, stainless steel. But here we are speaking about high entropy alloys. High entropy alloys are يعني new class of alloys that has been introduced, new class of alloys that have been introduced in يعني specifically for the scientific research community in 2004. Actually, two scientists, Brain Cantor and Jean Weye, these two scientists have put the main pillars or the main concept of high entropy alloys. But I remember from literature that some German scientists have, by trial and errors, some of the concept of this high entropy alloy, but they didn't. يعني how can I say, they didn't consider it. Also, we can find some of the ancient Indians tried to mix different elements, but the research of high entropy or the research of metals and alloy was not advanced in this time. So we can consider that the first two scientists that introduced the high entropy alloys was in 2004 by Brain Cantor and Jean scientists. The concept in these alloys are different for traditional alloys because we have at least five elements for high entropy alloys, and this system is known for its high yield strength and corrosion resistance. And you can classify them based on the configurational entropy, which is a function of the chemical composition or chemical molar concentration of the alloys. It can give you the configurational entropy of alloy. So what is the difference? If you can find, for example, for the titanium 64, we have obvious matrix of the alloy with some addition. We need to put some addition for this alloy to promote a certain characteristic. So we have interstitial or substitutional addition to the alloy matrix. On the other hand, for the equiatomic, if we mix it equiatomic concentration of titanium, for example, titanium, zirconium, niobium, tantalum, you have no obvious matrix, lattice distortion, and different characteristics will be obtained from this category. So we have low entropy, which is a traditional alloy, high entropy alloy, and we have the intermediate category, which is a medium entropy alloys. So what are the most effect or the base mark of this type of alloy is high entropy effect. High entropy effect, when we see the mixing into free energy of mixing for the alloy, we will find a very high value of the term TDS, and consequently lowering the delta G or the free energy of the solid solution. So a stable solid solution will be formed in this type of high entropy alloys. Sluggish diffusion and lattice distortion, these two effects, when we have different atomic size inside our alloy, so fluctuation in the potential will be opposing any migrant atoms, and consequently reducing the time. This will increase the time needed for an atom to migrate from one place to other place, and this will and this will in term of processing of high entropy alloy, we will need prolonged time, very prolonged time for making thermal treatments. And the cocktail effect, we are using at least 5 elements for the high entropy alloy, so the properties will be as a rule of mixture from the constituents element. Uh, we have main three categories that are composing the high entropy alloys, like transition metal high entropy alloy, refractory high entropy alloy, lightweight high entropy alloy, and it depends on the constituents element. If we look for the high entropy alloy and we try to pair between the biocompatibility elements and the refractory high entropy category, we can find most of the elements are biocompatible, excluding the vanadium and tungsten because of their toxic effect. We can find niobium, tantalum, titanium, and zirconium are all composition of the refractory high entropy alloy. So researchers have think about this type of alloys as biomedical implant, so we can get beneficial from the biocompatibility of these elements and high yield strength of this category to be used as a biomedical implant. But if you look in this table here, we will face the most important problem is the elastic modulus. So we spoke about elastic modulus as the most important characteristic. If you didn't consider the mismatch, you will deform your human, or we will deform the human bone. Actually, we will have a very high yield strength, and this is very useful for us because high yield strength means that we will reduce the implant size. But the elastic modulus with this severe value exceeding 100 gigapascals, so we will face a problem of mismatch, knowing human bone is around 30 gigapascal. So you think about the design criteria, and you will find for high entropy alloys, scientists think about experimental trials in the first or in the early start, as I told about the German scientist. You make your alloy and go for experimental procedures, and you take the result and analyze it, modify again, and repeat the cycle till you reach to the optimum results you need. And this way is difficult and cost a lot of money to reach certain property you need. Many simulation techniques and the calculation of phase diagram like thermocalc and mandate softwares, it will help you to make a phase prediction. But actually يعني for a new introduced category, if you are going to using calculation, thermodynamic calculation, this needs some experimental validation to be acceptable, or to accept the phase diagram, for example, obtained by thermodynamic calculation or softwares. It needs to be verified first, because in some cases we may face some foreign phases inside our alloy, but this is not defined or identified by the thermodynamic calculation. So يعني validation or experimental validation is required for using calculation phase diagram. Other techniques like AB initio calculation or atomistic techniques. Also, for the high entropy alloys, uh, titanium containing high entropy alloys, some of traditional alloy design criteria may be applied. If you are familiar with titanium alloys, you can use BOMD map, E over A, or in molybdenum equivalent. But this is in some time or in some cases not is not useful because it may find a deviation between the experimental result and your design. Finally, the artificial intelligence tool, and we can find the publication is progressively increasing till our days. We are in the start of 2025, so we will find increasing of the number of research going to using artificial intelligence tool. This is the first point. Artificial intelligence is increasing nowadays, and also uh, يعني for implementation of new artificial intelligence technique or simulation technique using artificial intelligence is not difficult. You don't need to know basics of, for example, thermodynamics or making molecular dynamic simulation. No, it's very easy and available. You know, you need to use, for example, the Python programming language, and library already exists, and you can choose the algorithm and you can go for your work. This is also exist in MATLAB if you need to use the MATLAB, so it's very available. But the most important problem that you will face in your working for artificial intelligence, using artificial intelligence in alloy design, is a data set. This is the most important. How you collect your data set, how you find your data set, how to make your data set uh, effectively working for your alloy design, filtering of the data after collection. This is the important, or this is the problem of AI. If you overcome this problem, you will find an effective artificial intelligence tool that you can use in your alloy design. For our case study, we have to define the problem as we in traditional alloys. You can find some toxic elements you need to evaluate, or no, you need to evolve new system. And for traditional alloy, you can find some properties are below the target. Also, for high entropy alloy, we have some problems. Is the difficulty of melting, and you should also, as a designer, think about the processing and the production of your alloy. You are speaking about equiatomic concentration, so you have at least 25%. If you are using four element, 25% of niobium and molybdenum and tantalum. If you are familiar with the melting techniques of these alloys, you will know that you need to reach to the melting point of tantalum to in the first run to reach to a full liquefying of your alloy. This also will be one of the most difficulties you will face, and you should consider it while you design your alloy. Also, the high elastic modulus of your alloy and the complication in the prediction. We will find a prediction يعني difficulty in prediction because the data set is not or insufficient experimental data that we can use in our prediction. And multi-phase alloy in high entropy alloy, you can find a multi-phases alloy. The high elastic modulus or the elastic modulus will be the point in which we will utilize our machine learning in the design of our alloy. These are the goals of the case study: to design low elastic modulus, high strength, high corrosion resistance, low melting temperature, and building an assistive tool for your work to be used as assistant for your design and fasten your design. The case study here, we depended on main three pillars. One of them is based on learning machine, is extreme learning machine. And extreme learning machine, we built this neural network. We use this neural network for the prediction of Young's modulus and hardness prediction. So we utilize the machine learning with our artificial brain in this case to predict for us the Young modulus and hardness prediction. And in my point of view, you shouldn't depend 100% only in machine learning. You should confirm your design using other techniques like the design parameter calculation using electronic parameters and single phase calculation. And this comes from the thermodynamic calculation and and phase diagram calculation software like ThermoCAD. You should support your extreme learning machine by different techniques, because our alloy is our category is newly developed and you will not find sufficient experimental data. Uh, about the built brain or our neural network, okay, this neural network, firstly, we trained it on a data set consists from titanium, zirconium, niobium, molybdenum, and you optimize for the number of hidden layers, and it gives you an output which is a material property. But the problem here, as we have stated previously, limited data. We don't have enough or sufficient data for high entropy alloys. So how can we deal or how can we build effective brain for the prediction of mechanical properties? The answer of this process comes from the neural network itself, the type of network itself. In our case study, we used a machine learning technique used extreme learning machine. In other techniques, you can make processing of the input data, because the problem in any neural network is the number of weights. Increasing the number of weights means that you need to solve for this weights, and more data is needed for the training and obtaining optimum weights. If you don't have sufficient data, so your network will not behave or will not work optimally in your case. In our case, the extreme learning machine. Yes.
Am I
Any
audible?
questions?
Yes, yes.
Yes, please.
Which software do you prefer? Which one is the best software for processing this kind of issue? Like
Your voice is not clear. Try to raise your voice, please.
which
Sir, I will repeat, sir. Professor Sehgal is asking that which software is best for processing this neural network operation to decide the. Uh,
Oh, okay.
hmm. What
For
type
my
of?
case, I used MATLAB.
Okay.
Yes, for my case, I have used my MATLAB. But in case you don't have a license for the MATLAB or it is difficult for you to access for MATLAB, Python, the programming language using Python and its libraries already offer these algorithms, and you can use it freely. It's open source, so you don't need to pay for this type of software.
in MATLAB there is a new toolbox. So did you use that?
The question is not clear. Sound, please, or someone
Yes,
repeat
yes.
for me.
Yeah. Please, Professor Shankar, please, your voice is not here. We are not
I
getting it.
am asking that there is a standard neural network toolbox. So, did you use that toolbox or you wrote a separate program for processing these neural
Yes.
networks?
Yes, I
Uh,
I got your question.
mm,
If, depend on the network you are using. For the extreme learning machine, I didn't found it in the toolbox. You just write your code, okay, with the
Okay.
assistance of some of computer scientists. Okay, you write your code and you start training your neural network. In some cases, if you, for example, you are using feed-forward backpropagation network that exists on MATLAB, and I think you can change the training algorithm from Levenberg-Madukra to Bayesian regularization and the gradient transition. Many training algorithms exist, and you can take the code from the toolbox. Okay, he can generate the code for you, and you can change the training algorithm for you. So I think the area is open for anyone to use the machine learning in his alloy design, especially يعني, but I don't recommend such type if you can take a consult from AI for writing the code for you, but you should drive the process by yourself. So regarding this question, the area is the ground is open for all alternatives.
mhm. Sir, if the data size is very, very low, then what is the solution?
No, please repeat the question, please again.
If the data size is very less available to us, so how can we get a result?
Okay,
Because
you should
already,
first
hmm,
uh, you should first calculate the number of effective parameters. Okay, depending on the
ये
effective
मेरा
parameters,
मीटिंग चल रहा है
you will control the number of neurons in hidden layers and the number of hidden layers
मास्टर्स डिग्री में करवा
to make your network optimally working with your data set.
सिटी पूरे भारत
hmm.
Okay,
Okay, okay. Yeah, I
so
got
the quest, yani the data set will control the structure of the neural network.
it. Mhm.
Mhm.
Okay.
Okay, so an extreme learning machine, as we have said, that these weights are obtained randomly. He randomly assigns the weights between the input layer and the first hidden layer. Just
one candidate
solve them mathematically for the second weights between hidden layer and output layer, and make a comparison between the output, predicted output, and the true output. And many iterations are, and you control the number of iteration in this case till you reach to the minimum error between output and true output or the experimental output of your dataset. This is the first point, so that we will maximize the benefit of our data set, and in the same time, why I should design for high entropy alloy where I can design for medium entropy alloy, and medium entropy alloy have the same characteristics for high entropy alloy, but it differ from the high entropy in the number of constituent elements. 3 or 4 elements are enough to start your medium entropy alloy, and it is in a common borderline between traditional alloy. So you can feed your dataset by traditional alloy, and in this case, you will maximize the number of your data point in your dataset. So these are the two techniques that I
Uh,
have depended on them to increase the number Yes.
Okay. Please, sorry to interrupt because your topic is very much interesting. So the participant is asking the question. Can I them?
Yes, please. Any question, I'm
Uh,
ready. Yes.
yeah.
Yes.
So and the question is, any data pre-processing is needed for machine learning model?
Of course, you need to process your data manually first, and I will tell you how. This is for my case. Yani I do this in my work. Okay,
Okay.
you just, as you see in my data sets here, you collect everything regarding your data set. The chemical
Okay.
composition, of course. You
Yes. Yes.
calculate for the
This.
configuration and
Yes.
entropy table.
Dear
I
participant,
am
please
answering the
wait.
question, but
Yeah. Okay. Okay. Hmm.
you record everything regarding the dataset, the condition, the phase, and testing type. For example, for hardness, it's nano indentation, or for, sorry, for elastic modulus, for tension, or obtained by bending. That's why you finished your training and take the prediction. And for example, you make 5 runs of the prediction. You train for 5 times and take the predicted output and make a comparison between the experimental and the predicted value. For example, if we make 5 runs of training and take 5 times of prediction, I found that in some of composition, I found a deviation between in the 5 times between experimental and prediction. This may return back to incorrect results that was supplied by the author itself. Or, for example, I'm speaking about single phase, and I found in my study alpha phase give a wrong prediction, so it disturb your neural network. You should process them firstly manually and exclude incorrect composition or out of يعني, the data that is out of your system. For example, different phases or precipitated phases exist. So you can highlight this from the comparison between the experimental value and the predicted value you take from the neural network. I hope I can your question has been answered from this point. Other processing, of course, is accomplished in case of limited data set, and this exists actually in our second case study. Any questions?
Am I audible? Am I audible? I just wanted to inform the delegates, participants that you can unmute yourself. We have updated WebEx settings. You can unmute yourself in the questions. And please ensure that after raising your query, please do mute your mic so that there is no noise or sound from your side. Thank you, everyone.
So I will repeat as Professor Shankar Sehgal is announcing that we have updated the settings. You can unmute your mic and ask the question one by one. And after finishing your question, please mute your mic. Okay. Sir
Okay,
Noor,
if no
you
question,
continue, sir. Continue.
okay, now everything is recorded about dataset, so we can make processing and filtering of the data till we reach to the optimum size of dataset. For example, we have two neural networks, two independent, okay, two networks, one for the hardness and the other one for elastic modulus, because we need low elastic modulus and high yield strength, high hardness. So two regressors were built. Each contain around 130 data points. After reaching to optimum training conditions, and now our neural network are testing, the testing error is very low. We start to feed our neural network, or in simple words, we start to ask our neural networks for different alloy systems. Every line in this control represent an alloy system. What will happen for the elastic modulus if we increased the molybdenum, if we reduced the niobium, if we increased the titanium? These graphs give us a clear answer for the change in chemical composition. This answer comes from the machine learning itself. We excluded one system, for example, the titanium 44 zirconium X, niobium 51 minus X, molybdenum 4, and we can find a region. In this region, we have a low elastic modulus with the blue line and high hardness. This will give us a high elastic admissible strain region, and is a ratio between the elastic modulus and hardness. And this is very optimum alloys that could be used for orthopedic implantation. So your composition should exist in this region to get low elastic modulus with high yield strength. These are the details of the two neural networks, one for Young's modulus and the other for hardness. And we represented the prediction of these two neural networks in color contour, and we can find the lowest elastic modulus exist on around in the blue region here. Okay, 48% of titanium and 35% of zirconium in this region, corresponding to the same region of reasonable hardness value. The first part we have discussed here relating to the elastic modulus prediction by machine learning, or the answer of machine learning to what we need. We need low elastic modulus, high hardness, and the machine learning has answered us in this point. But as I told you, don't depend 100% on the machine learning itself. You should go and study the other design parameter or the classical design parameters rules. You should support both. The benefit of the machine learning is to fasten your design process. But for my point of view, you shouldn't depend 100% on this technique. You should revise the classical design rule at the same time. We depended on the design parameter calculation for the valence electron concentration and the bond force between the constituent element inside our alloys. If we calculated this bond force and we study the relation here, the experimental value to the valence electron concentration and the corresponding bond force and the constituent phase. Okay, for most widely used high entropy, medium entropy, or traditional titanium alloy in this table, and we plot the relation between the elastic modulus and bond force and valence electron concentration, and we could find that lowering the bond force in a BCC phase and lowering valence electron concentration in BCC phase will ensure for us low elastic modulus. Whereas if we allow the precipitation or coexistence of secondly high hexagonal closed packing HCB in our alloy, increasing back again for the elastic modulus. So this is the benefit. This is the benefit of studying classical rules. Also, for this composition, we have consulted our built brain in two figure in C and D, and he gave us the same trend. We just feed him by the chemical composition, and he gave us the predicted elastic modulus, and we found that lowering the bond force and lowering valence electron concentration sure will give us a low elastic modulus. So we have two answers. One answer are brought by classical rules, and the other answer are brought by machine learning. And this will give us a conclusion for our final design. The conclusion stated that your alloy should be a single BCC with low valence electron concentration lower than 4.2 and lower than or around 1.6 in the bond force and in BCC phase. Okay, if you plot a phase diagram in titanium 48, and this region was strongly recommended by the machine learning, and you go for the thermocalc software to draw the phase diagram, he will give you this phase. So what you conclude from this phase, actually, we have allocated three compositions in this region. Why in this region? We have stated one of our problem is the high melting point of these systems, because we have niobium and molybdenum. Okay, niobium will increase our melting point, but if we increase the zirconium content, we will allocate our alloy in the low melting point region. So you should consider this. Also, a low Mashi zone. Low Mashi zone will reduce the segregation inside our alloys and the columnar and the dendritic structure. So you will reduce the segregation in your alloy. Region of BCC, and as you know, the machine learning recommends and the classical design rule recommend existence of BCC beta phase. That's why we should follow the production of the as cast state by a solution treatment to stabilize the BCC single beta phase. Okay, these are the final composition with the calculated bond force all around 1.6 and valence electron concentration around 4.2. Okay, for the experimental procedures, as you can see, we make arc furnace casting using arc cast 200 is the model of the device, and this is the most important rule. Now, in this step, you obey the structures or the instructions comes from the classical rule and the machine learning, which states that you should stabilize the BCC beta phase. Okay, we make a deformation 40% cold rolling for the alloy, and we accomplish a solution treatment at 1000 centigrade Celsius to stabilize our alloy in this region or a single BCC beta phase. Okay, so now the machine learning is the drive the process itself. Going for the testing and characterization, now the design step has been terminated, and now we are characterizing our work. Will it be suitable for orthopedic implantation or it will go out of our target? As you can see, a minor amount of dendritic structure, and after solution treatment, the beta grains has appeared, and the XRD confirm a formation of a single BCC beta phase. Okay. Also for the compression test, and we accomplished or the compression. Yes, any questions? Okay. Also, we have accomplished the compression test because also orthopedic implant are exposed for compression loading all the time. Okay, and you can find that a plastic deformation flow occur after the yield point for the all designed alloy. So our alloy has a good ductility with a high value of yield strength, and this was recommended for us, and it can be found that it is higher than the commercial pure titanium or 316 stainless steel and more than some of the traditional titanium alloys. Uh, for the elastic modulus, both of three alloys, especially the zirconium 40, which is our focus, is around 69.5. The red line here, or the red column, indicates the experimental value, which is very near to the prediction of the neural network for both three alloys. Any questions?
Professor, I have one question. That
Yes.
zirconium, you have considering a variation in a zirconium to design your alloy, but you have
Mhm.
niobium and molybdenum is also. So why you are not considering the variation of composition in niobium and molybdenum?
Okay. The answer of this question is here. You
In
can
a
find
new,
that the variation in the
okay,
make
okay,
يعني
yes,
a drastic elastic modulus when
okay,
compared to the niobium content itself. Okay, moving both in this region, you may make the niobium concentration varying while stabilizing the zirconium, but you will not affect the elastic modulus. So zirconium was the most element that affect the elastic modulus of alloy, in line with the melting point. Increasing zirconium strongly affect the bond force and affect the melting point of the alloy. So we
okay.
consider it.
It's a
Uh,
significant contribution in.
yes. Any questions?
Okay, please
Okay.
continue, Professor. Hmm.
Okay. Here also you can get an indication about the H over E, or the hardness over the elastic modulus value, and it is very high for the produced alloy, which give an indication about the wear and abrasion resistance for the produced alloy. The magnetic susceptibility linearly, or when you make a fitting, okay, no saturation behavior exists, so the alloys are a paramagnetic alloys, okay, with values lower than the commercial pure titanium or titanium 64. So you successfully, or we have successfully achieved a low magnetic susceptibility. For the corrosion resistance, which is important for us, is the passivation behavior. So our alloy passivate in this region. Okay, so a passive layer will be formed in our alloys and low corrosion rate, and this is very important for long time duration and dimensional stability of the emblem. Actually, you should accomplish your test in a solution that imitates the human body fluid, like phosphate buffer saline or Ringer solution to be injected inside the human body in case of dehydrations. Also, you should stabilize the cell temperature. Your cell temperature should be around 37 centigrade Celsius to simulate the implantation environment. Also, the oxide layer you should analyze using XPS, and all are biocompatible. Oxide layer consists of titanium oxide and zirconium and niobium molybdenum oxide after fitting the spectrum of the XPS. Final and the most important test is the cytotoxicity, which will tell you if your alloy is toxic or non-toxic to the human body. Is cell culture. You culture cell on the surface of your alloy and incubate it for a certain duration of time. In our case, we used firstly the oral cell, normal oral cells that exist in mouse in case of dental implantation, and we can find that no toxic effect has been caused for our alloy, nearly low toxic effect around 2.7 for percent when we compare it to the control cell, which indicate يعني a good viability of our alloys. We repeated the test also, but in this case we used the osteoblast test, osteoblast cells, and these cells are responsible for building the human bone and will be intact to the implant, and we can find a very well health cells that exist on the surface of our alloy, especially the zirconium 40 with a viability reaching 89.17 when compared to the control well. Now I can go for the second case study if you have no questions.
And unmute your mic and ask the question.
Good evening, sir. Sir, I have a question, Dr. Noor.
Yes.
Okay.
Yes, what I wanted to ask is there is a topic in biotechnology. We generally call it bioremediation. In that topic, we study the higher concentration of different metals they accumulate within plants and animals and fishes too. For example, nickel or chromium, or to a higher concentration. At that higher
Yes.
concentration, they behave like a toxic material. Now the alloys of different materials present outside in the world, do they have the same characteristics they are present in the biomaterials or in the plants or fishes, or they behave some different?
You ask about the pure metal or these oxides?
Yes. I am asking about the different properties, whether they have the same properties, whether outside the plants or in higher concentration within the animals, they behave same or they behave differently. Any idea?
Actually, I have no idea, but your answer can be your question can be answered from the cytotoxicity evaluation. We confirmed the
Okay.
formation of these oxides, okay?
Okay.
And
Okay.
after incubation for 72 hours or 10 days, they have no dramatic effect on the cell culture and the proliferation. Okay.
Okay.
Actually, this compound consists of the metal and its oxides, and I don't think they negatively affect the cultured cells.
Okay.
But for يعني 100% correct answer, it should be studied in lab scale.
Okay. Thank you, sir.
Okay,
Thank you.
you are welcome. Okay, going now for our case study 2. Now we successfully have achieved low elastic modulus around 70 gigapascals, but we need to reach to a lower, a more lower lower elastic modulus. And we consider that the base we have is titanium. After we have excluded molybdenum, titanium 49, zirconium 40, niobium 11, and we look that uh, if we destabilize the beta phase a little, okay, by adding some of the alpha stabilizers, and we consult the calculation of phase diagram about stabilizing the beta phase, so we can achieve a low elastic modulus. We consult the phase diagram, and we have plot after we choose silicon. Okay, we excluded aluminum because of its negative effect. We make a calculation for silicon and tin. Okay, and we have two phase diagrams here, one for the silicon and the other one for the tin containing alloy, titanium, zirconium, niobium base. For two important points, we have existence of intermetallic M3Si1 with the BCC phase, and as I have said in the earlier start, these intermetallics will affect the ductility of the alloy and consequently will not be optimum for orthopedic implantation. However, for the tin containing, if we stabilize the BCC beta phase around 1000 centigrade Celsius, we can add up to 3% atomic of the tin to our alloy. Okay, so in this case, in both of the two cases here, we will not depend on the silicon because it is not suitable for our case, and we will use tin in this case. Coming for the machine learning or the pre-production prediction, we need to consult again the neural network, but in this case, we have added alloys that contain tin to our alloy. If you remember, we have 5 inputs in the case study 1. Now we have 6 inputs. Okay, so we have built two independent neural networks, feed-forward back propagation neural network with BCA, and the other one is extreme yielding machine. So what is the meaning of BCA or the principal component analysis? This technique study the dataset and the input of the dataset, and you can reduce the number of input input to the dataset, which is a chemical element. You can exclude 1, 2, or 3. You can select this in your study. Okay, and in this case, you reduce the dimensionality of your dataset and maximizing the benefit of your network. For example, if you have a 3D drawing in 3 dimension, you can express the same drawing but in 2 dimension by making 2 views of this object. This is the same thing which BCA or principal component analysis can accomplish to your network. But in this point, you should take in your consideration that as you accepted minimizing the number of input of your dataset, for example, we are speaking about titanium, zirconium, niobium, molybdenum, tantalum, and tin, 6 inputs. It will be reduced to four input, as in our case here. So the algorithm itself excluded some of the input data set, which actually some input that is not directly affect the output of your neural network. So you will expect some of sensitivity reduction of your data set, or sorry, for your neural network. This is the case in the BCA. After we successfully train both extreme learning machine and BCA for the yield strength prediction and elastic modulus, we run our prediction and here for our proposed compositions that will stabilize the BCC phase and the prediction of two neural networks with respect to the experimental result for the compositions that exist in literature here, and we can find that the neural networks for both hardness, for both elastic modulus and yield strength behaving well in well behavior for our case. Just we need to characterize our alloy and we will stabilize the BCC beta phase at 1000 centigrade Celsius, and we will repeat the magnetic property we successfully, after making solution treatment, has stabilized a single BCC beta phase for the 10 containing alloys with a higher elastic modulus, as usual, higher than traditional alloy. And the most important, that we have successfully reduced the elastic modulus to around 55 gigapascal, which is very, very important for our case. Okay, but you can find there is an inflection, and from literature you can, for titanium based containing alloy, a BCC beta phase can obtain a low elastic modulus. But if we can obtain this minimum point at lower valence electron concentration for binary alloys, we will obtain a lower elastic modulus. But in our case, we have shifted this lower peak to a lower valence electron concentration, and this was the target of this study, is to reduce the elastic modulus, and we faced this inflection and increased back again. This may be most probably due to precipitation of nano precipitation phase like in such type of alloys. Here you can find a comparison for the proposed three alloys. In the black line here, you will find the inflection in the elastic modulus, but neural network cannot catch the type of inflection. Okay, the extreme learning machine, the first neural network cannot catch, and it expects that adding more 10 will reduce the elastic modulus of the alloy, whereas the feed forward backpropagation incubated with BCA mostly cannot detect any different or any changes in the elastic modulus. And this is because I have told you that incubating BCA to your machine learning algorithm will affect the sensitivity. It cannot differentiate between this small differentiation or small amount difference in chemical composition. But different level of alloys or different composition or containing elements, it can catch the difference in elastic modulus. This is point number one. And another point regarding the equiatomic titanium, zirconium, niobium, tantalum, okay, in the yield strengths, the experimental value are around 1000 centigrade Celsius, whereas the prediction are around 1400 megapascals. Actually, after I have searched for this alloy, I found that I have feed it in my dataset in as-cast state. But in some research, if you're gonna for annealing for this composition, it will reach to the prediction of the both neural networks. So why this come, or why this happen in our alloys regarding the inflection that happens in the elastic modulus? It return back to the distribution of constituents elements inside your dataset, and you should study this in the first or the early point of your initiation your neural network. For the elastic modulus, we can find that the meta-stable beta phase or beta plus alpha double prime is around 5% of the whole data set. That's why the inflection is not followed by the neural network for the three alloys. Also, for the yield strength, the average relative error is high, around 20%. And as you know, as a metallurgist, you know that the yield strength is affected by many factors that can affect, for example, the grain size, the number of dislocations that exist in the alloy, the affinity or the oxygen content inside your alloy. So it is difficult to build a very accurate machine learning system that can predict the yield strength of your alloy. For the cytotoxicity, we can find that our alloy, because we selected a biocompatible element, okay, we can find a health cells that exists. This is the nuclei of the cell, and this is the full the full cell, okay. And we have a hydrophilic effect of the surface, so we have obtained a very high cell cell viability for both alloys. Finally, to make our work يعني effectively working, okay, or can be accessible for all user, you can take your code and make a standalone application. In this standalone application, you can feed your chemical composition, and it can calculate for you the expected elastic modulus and expected yield point. Actually, I have built this application after the first case study, and it was very beneficial for me. You can imagine with me that for my case in my lab in Egypt Japanese University for Science and Technology, it will take me around 1 week for production and the processing of the alloy, and at least 1 month for testing. You are, if you are dealing with around 5 composition, you will take at least 3 to 4 months to get your results and start to analyze them. But in case of existing this tool, you can just go for the standalone application and make your calculation, and you can predict the expected elastic modulus and yield point, and you can modify your design till you reach the optimum 2 or 3 composition and make them in one run, and reducing the time needed for testing and the characterization, because you are working to the point or to the effective point you need. Also, this software can detect if you put the composition lower than 100 or more than 100 Bers, or if it is out of the effective range, or if it is not a beta phase, because I have stated previously if the alpha phase exists or alpha beta composition, the the neural network will not work effectively, and the error will be uh, very high in this case. Finally, I'd like to acknowledge our collaborator in both two case study work in Egypt, okay, and IHME University from Japan. And finally, thank you all for your attention and for your listening to me. Thank you very much.
This presentation, Professor Noor. Uh, in fact, very informative and new method to design an alloy. Participants, if you have any question, please ask to Professor Noor.
Good evening, sir.
Yes. Good afternoon.
My query is, you have successfully built a GUI, graphic user interface for the
Yes.
MATLAB. So
Yes.
how you which programming language you have used? Secondly, front end and back end. Have you clubbed in the Windows operating system or Linux or Unix or anything else?
If I have got your question, you have an application toolbox in MATLAB, a GUI. You can launch it
Okay.
and you can build your own standalone application.
Okay.
This is easy if you
Okay,
have the
sir.
code and it is working correctly.
Okay. Do we have to make our own code ready before going in for such kind of jobs? है ना?
Yes, because if some functions or you are calling some functions in the code itself, you cannot use it directly to the standalone application. Just you will
Okay.
increase your code, put the function inside the code itself, and it will run normally.
Okay. Okay, sir.
It was also recommended by Professor Noor that you can also take a help of AI to build a code for your own.
Yes, sir. Yes, sir.
Hmm.
Yes, sir. Thank you, sir. Thank you.
You are welcome.
Good evening, sir. Am I audible?
Good evening.
My question is this user interface, is it say some exe file or some other uh, format it is? So suppose we have to share it with someone. I have a code. I want to make a user interface. So when I will be sharing it with it other researchers, so in what format
No,
it can be?
it is a normal application. It's a normal application, and he will not reach to the code of your code. Just he will
Uh,
use the input and output.
right. So it has to be installed like any other software.
Yes, yes. Just the user need to install a MATLAB runtime. It's something like a mini application of MATLAB. MATLAB runtime, he install it in his device, or if when you finish your building your standalone application, the installation of this application will automatically install MATLAB runtime in the device. You just supply him with a device and the install icons. He will launch it and it will install everything in your device.
Right. And is there any other way to make it run on Android, like or web application, so that it can be shared globally?
Actually, I have no experience about the MATLAB, يعني, Android application, but I think if it is built on Python, it will be available to be programmed on Android devices, because you know MATLAB and Python are the same syntax, nearly same, I think.
Right, sir. Right, sir. I have one more question, sir.
Yes, you're
It's about the neural networks. So, as I could see, there were only 150 or less than 200 data points.
yes.
Were they used as input for artificial neural network?
No, repeat the last question, please.
My question is, when we work with the neural networks, so the number of data points we need is very high. So how
Yes.
many data points we used in this work? You used in this work?
I think it's around 140, something like this. But whatever the data you have, okay, you should control the structure of your neural network. Okay. For example, if you have total number of weights in neural network around, let's say 100 weights, okay, and you select 20 point for training, this is incorrect. So you should optimize your structure of your neural network to be covered by the training dataset, and this is what I considered in my work.
Right, sir. Right, sir.
Okay.
Because I was also using machine learning for my glass ceramics, and I had around 500, 600 data points, but the performance of my own neural network was very poor. Well, when I shifted to some other models like random forest or extreme gradient boosting, then it gave better
Uh,
results. So
yes,
that's why I was asking.
you should make a switching for the training algorithm. In some cases, the neural network is not well trained, and I have some experience in this point with one of my colleagues who was working with conditioning systems. We have successfully initiated the neural network, but after making a lot of trials in the training algorithm. So the training algorithm itself effectively solve your problem. So you should change the training algorithm, training rate, the number of neurons. All these factors affect your performance of the neural network.
Right, sir. Right, sir. Thank you so very much, sir. Thank you.
You are welcome.
So one question in a chat box is that in a spine implant, how the machine learning is used to design the rods, plate, tail, patient-specific spine curvature. So here I want to answer it that this presentation is only for designing the alloy only, a new design. But in order to design the rods or curvature, we need something different type of an approach according to the patient specific requirement. So in our previous days, in our 18th August, Professor Shiva has given the idea about this, that how can we design the rods or the plates for the patient specific spinal curvature. So this lecture given by the professor is only related to the design of alloy. Any other question, please?
Sir, I have another question. Dr. Noor, good evening, sir.
Good evening.
Sir, I wanted to ask in mid lecture you have told effective use of AI tools for alloy designing. It is possible only when you have collected your data set.
Yes, you
So,
should have.
do we have? Yes, sir. Sir, do we have any setup or protocol the way how we can collect enough amount of data set for moving into this particular field for
Actually,
using effectively AI tools.
this is a very good question, Dr. Vikas. Dataset is a very problem in initiating any machine learning. And to solve this problem, you have two ways. Either you can find some of researchers that have worked in this point, and they can supply you by the dataset, and you can take it, modify, or update it. Okay, this is the first. But in case you cannot find, and that what I have done in my work, you go for the literature and start from 20, for example, 2025, and going for older and collect from literature the data needed for your work. For example, I am searching for elastic modulus and yield
Yes,
strength,
sir.
so I go for literature, read everyone, and get the testing technique and write it down in my dataset till I have built not 100% effective dataset, but at least 80% or 90% effectively working dataset that will help me to fasten or making the design process fast.
Okay, sir.
Okay.
Thank you, sir.
You're welcome. You're welcome. Any questions?
I think, Professor Noor, you have answered all the questions very nicely, and
Thank you.
almost time is running, but we have a lot of things that we would like to learn from you. Uh, Now, I think the next lecture
Thank you very
is
much,
for the
Prof.
next
Seto,
lecture.
and actually, thank you
Yes.
very much for this nice invitation.
Thank you, Professor Noor. And dear participants, now Professor Saikal will introduce our next expert. So please over to Professor Shankar Saikal.
Thank you, Dr. Sidhu. Uh, Good evening to all. It is my proud privilege to introduce Dr. Anupam Agarwal, the resource person for the next session. And Dr. Anupam Agarwal is a professor in the Department of Mechanical Engineering at Indian Institute of Technology, Ropar, that is IIT Ropar. He received his bachelor's degree in mechanical engineering from Madan Mohan Malviya Engineering College, Gorakhpur, master's degree in mechanical engineering from Indian Institute of Technology, Kharagpur, and PhD in mechanical engineering from Indian Institute of Technology, Kanpur. He worked as a postdoctoral fellow at International Center for Automotive Research, that is ICAR, at Clan, United States of America, before joining IIT Ropar. His research areas include manufacturing processes, particularly die-less forming processes such as incremental forming, deformation machining, deep drying, CAD/CAM, and additive manufacturing. And today he will be taking a session on engineering of advanced materials and design for biomedical applications. And Professor Anupam Agarwal, Dr. Sidhu, has he joined?
Yes, sir. He is joining. He is joining, sir.
Please let me know as soon as he's joined. So I will make him the co-host, and I'll send the presenter rights also.
Okay.
And in the meantime, I would like to again inform all the delegates that if you have any query, you can please unmute your mic. And actually, I also apologize because earlier the meeting settings was such that your mic was actually locked. That is the default setting which is provided by default in the WebEx software which we are utilizing for this meeting. And this time we have updated the settings, and you can now easily unmute yourself, raise your query, have the discussion. And the request is that you please do not forget to mute yourself after raising the query. Dr. Anupam Agarwal has yet to join. We are just waiting for him to join.
Sir, Professor Agarwal informed me that he will join within 5 minutes, sir. Because he got some issue with the network. Within 5 minutes, he will join, sir.
Yes, sir. Fine, fine. Perfectly fine. No issue at all. Actually, this is the advantage as well as limitation of this online course. The advantage is that the course you can easily attend in the comfort of your home, and even during evening hours by sitting at your home, you don't have to really travel a faraway place to listen to the expert across the globe. And the limitation is, of course, the network bandwidth. It is really a limitation. Sometimes, yesterday also, I was trying to unmute myself and I was not able to do that. That was, I think, due to some network issue itself. Yes, I am receiving feedback from the delegates. Dr. Satwinder Singh is saying very informative. Thanks, sir. Thank you for your feedback, sir. And Dr. G. Suresh has written in the chat box, very informative. Thank you, sir. Thank you so much for attending.
Sir,
Dr. Satwinder Singh saying, yes, he has
sorry, sir.
joined. Yes, sir. Yes.
Professor Anup Agarwal has joined the meeting. You please give the rights. And before that, can you please again give the introduction about, sir?
I will do. Very
Hello.
good evening to
Good afternoon, everyone. Yeah, am I audible?
Yes, sir. You are very clearly audible.
Okay,
Good
thank you,
evening,
thank you,
sir.
thank you. Please go ahead. Good evening.
A very good evening to our resource person of this session, Professor Dr. Anupam Agarwal from IIT Ropar, and my dear colleagues, delegates, faculty and students and volunteers. It is my proud privilege to introduce once again Dr. Anupam Agarwal from IIT Ropar. He is a professor in the Department of Mechanical Engineering at Indian Institute of Technology, Ropar. He received his bachelor's degree in mechanical engineering from Madan Mohan Malviya Engineering College, Gorakhpur, master's degree in mechanical engineering from Indian Institute of Technology, Kharagpur, and PhD in mechanical engineering from Indian Institute of Technology, Kanpur. He worked as postdoctoral research fellow at the International Center for Automotive Research, that is ICAR, at Clemson University, United States of America, before joining IIT Ropar. His research areas include manufacturing processes, particularly die-less forming processes such as incremental forming, deformation machining, deep drawing, CAD/CAM, and additive manufacturing. And today he will be taking the session on engineering of advanced materials and design for biomedical application. On behalf of the organizing team, Chandigarh, and Sardar Byan Singh State University, Gurdaspur, the Department of Mechanical Engineering of that university. The FDP coordinator, Dr. S.S. Sidhu from that university, is also here in this meeting. On behalf of the organizing team, I would like to welcome you, sir, and I would also like to thank you for ceding to our request for taking out your precious time in delivering this lecture, which will be really motivating and benefiting to all the delegates as well as the organizing team also. Thank you, sir.
Thank you so much.
Thank
Yeah, thank you so much for nice introduction. And yeah, like I'm hoping like that I'll be able to deliver to the expectation of the audience and to the organizing committee. I'll share my
Yes.
screen.
Yes, sir. You can click on the share button and then you
Okay.
PPT.
Okay.
First, you need to run that slideshow in your PPT, and then you can start sharing. So,
Is it visible?
yes, your entire screen is visible now.
Okay. So now this full screen thing.
This PPT file is visible. Please click on the slideshow mode. Yes, the first slide showing your beautiful
Okay.
campus that is
Yeah.
visible now.
Sure. Yeah. Thank you. So we can formally start now.
Yes, you can
Yeah.
start.
So yeah. Sure. So thank you once again, the organizing team, for giving me the opportunity to interact with the audience and then deliver a lecture in the ongoing 1 week online AICT Training and Learning Academy, this faculty development program on next generation biomaterials, clinical translation through machine learning. So the research areas, as you came to know, mainly is manufacturing and then sheet metal forming, additive manufacturing, and so on. So, like one of the domain that we are trying now, which is closely related to the theme of this FDP, is trying to develop some new biomaterials which can then be reprinted using some of the advanced techniques of bioprinting. So the title of today's talk, in line with that, is synthesis and engineering of advanced materials. So step is to develop such material and design it for some biomedical application. So what we are trying currently is for some implants or some bone-like structure. So I'll present that in my today's work. And yes, very rightly said, Professor Cycle, that like this is the beautiful campus of IIT Roper. So like the view of that is quite impressive, and then I welcome all the participants if you visit our campus. Coming to the introduction of the slide of my talk. So like most of the researchers, they try to mimic what nature has already made. for our case, what we were interested is to make like to do two things. One is to mimic bones. Like there are several key things in our body, muscles, fats, bones, and other things, and then like all of that are equally important. What our focus was that the bones, which contain about 50 to 15 to 20% by weight, if we like, and then most of the times we hear that like some fracture of the bones or the bones are losing the strength and so on. So we wanted to just kind of dig into what kind of material it is, what kind of structure it has. So what we from the literature found that bones generally consist of this flexible matrix and some bound minerals, which are, I'll just put some highlighter on. Okay, maybe this itself is okay. This cursor is fine. So this flexible matrix 30% and then minerals 70%. So the flexible matrix, that is 90 to 95% some fibers, these collagen fibers, and remaining is some other substances. So this elasticity of this collagen, it improves the fracture resistance. So if that reduces the chances of fracture increases, and the matrix is hardened by the binding of inorganic mineral salt, that is calcium phosphate, in a chemical arrangement known as calcium hydroxyapatite. So this calcium hydroxyapatite is the bone mineral which gives it the bonding properties, and it gives the bone the rigidity that it has. So this is something which we found that, and then we wanted to make a biomaterial or develop a biomaterial which is based on or which contains this calcium, this hydroxyapatite material. And then the structure of the bones. So coming to the structure of the bones, so outside of the outside bone, this cortical bones, it is like the harder part compared to, and then the inside these trabecular bones, they are little softer ones. And then if you see, there's a gradation from outside denser to inside little porous or quite porous. So that means it is not just combination of materials, it is also combination of structures. That means the design also varies, the porosity also varies. So the kind of approach, in if we talk in terms of mechanical engineering, so it has two things. One is the development of materials and making some graded material, graded structure out of that, so functionally graded structures. So both of that we have attempted to mimic, which was there already in the nature. Our aim was to kind of like do some like research on bioimplants. So we found that what are the bioimplants, how do we define that? So like there are some basics like bioimplant. It can be defined as a prosthesis used to regularize physiological functions. They are made of synthetic biomaterials. So these bioimplants, they are made of some of the synthetic biomaterials. When we say biomaterial, any biological or synthetic substance or combination which can be introduced into the body as tissue as a part of implanted medical device to replace an organ or to support bodily function or something. So one of the key things that the biomaterial must have, there's a slide on that as well, that is biocompatibility. That means we cannot insert any material inside our body. We have to, like, the material has to have the compatibility with the biosystem, the body of the person. There are different biomaterials, different class of biomaterials which are there. For example, like metals, polymers, ceramics, and then some natural biomaterials just like this calcium hydroxyapatite. There are kinds or varieties of implants, because like particularly we are focusing on bone related things. So like several implants or some fixation devices, fixation implants, which are either made of metals or any of the materials which are biocompatible. Continuing to this, like this bioimplants, they are classified into different categories depending upon risk involvement and then what kind of review that is required. So the bones for which we were focusing, and then we saw from the introduction, this uh, bone has the kind of structure. So this bone comes under load bearing bio implants. So this load bearing bio implants, they fall under class 3 category of medical devices, and all these class 3 devices must undergo some sign of the devices in order to develop some material and uh, see if anybody has any question, like you can just stop me and ask, no problem. So yes, it's not that the material we develop or the implant that we develop will come to the market soon. It requires a lot of detailing, safety, and other reviews, several approvals before it comes. So patient devices, scaffold, and cup, femur bone, and so many. So which are under the class 3 biomedical devices. Now, one of the yes. Okay. One of the things that plays a role is the porosity of the scaffold, because what it allows, like, see, traditionally, like, the implants were just supposed to support the bone or support the organ. Now the next generation scaffolds or the to achieve is that some growth, some tissue growth in that, for the, like, what it will do, it will help the body, like, it will help that bone or other thing to heal itself. So so porosity is something which helps in or it gives way to the cells and tissues to grow through them. So this porosity or variation of porosity as per the requirement is one of the key things in bioimplants, and people are now focusing on making porous scaffolds, and then the implant which can kind of let when you insert it inside the body slowly, like you remove the implant later on, it will just get dissolved or absorbed, not dissolved, absorbed in the body. The reason is good because, like, the market, global market scenario, like, even though we do not want that all accidents to happen and all the diseases to happen, and then the need of implant, but over a period of year, bioimplant market has reached quite a big value. This was the data in 2020, and then the expectation is that the market will grow at a cumulative annual growth rate of 8.5%, and then reach a very high value. That means the requirement of these bioimplants will increase, and then there are categories, different categories of bioimplants in cardiovascular, neurological, orthopedics, dental surgeries, and so on. So, like, the market is there, and the need is not just to supply bioimplant, but to do in two ways. One, it is like to have it which can be absorbed, at least allows for cell and tissue growth. The other requirement, which is even more critical, is you or provide the bioimplants which are patient specific, because the femur simple this bone fixation devices or the femur implant, which may be good for one person, may require a different, like, the slightly different this topology for the other patient. So if we can do patient specific solution, or we can provide patient specific solution, is something which the customers, or like the patients rather, they are like, they are kind of demanding that. So continuing to this, like, this development of biomaterials and how do we approach that. So there are different several proper that what it should have or it must have is good mechanical properties, compressive strength, because most of the time bones are undergoing the compressive loading, good fracture toughness, corrosion resistance, like if it is of metals. So like what we want is that when the implant is with the or in contact with the bodily fluids, it should not corrode. It should have better tribological properties. Should have definitely this biocompatibility, and then if it has bioresorbability, then it is. So there are several candidates that are there, and then some of those which we shortlisted were titanium, stainless steel, magnesium, and its alloys. They are quite widely used in metallic biomaterials. However, take part in healing process. High energy absorbing metallic implants, they are also used to support fixation as well as replacement of damaged load bearing parts of human body, hip, cup, knee joint, etc. There's a video, I'll play it maybe after 4 or 5 minutes once we are done with the introduction. What it actually has is what is expected implant. So once we are just done with the introduction, I'll present to you this video. So in order to kind of growth and options which people try, one of that is a metal ceramic biomaterial. So the one which we have tried attempted in our work. So what this does is like different bioceramics. One of that is hydroxyapatite. If you remember, like at the beginning slides, we presented that it is an important mineral of which is present in the bone. So which is a bioceramic. So different bioceramics, they have very good biocompatibility. And being a natural integral part of natural bone, different phosphates, they are used to make the metal ceramic composites in order to do what? In order to enhance the biological properties. The mechanical properties were very good already in metal implant, but if we mix them in the correct amount, correct quantity, we can increase the biological, we can enhance the biological properties of the biomaterial. And then there are challenges, like the it's just not that like the metal with metal probably is okay, but metal with ceramics and then bonding becomes very difficult for metal ceramics based composites. The fabrication is quite challenging. So like some of the common methods which are there, like powder metallurgy. So some initial samples we prepared by this powder metallurgy using microwave sintering. There are other alternate ways like spark plasma sintering as well we can do. Casting is another one, but it is like the difficult when we want to mix it in different quantities, and then we want to make the graded structures. Additive manufacturing is one of the strong alternative to fabricate this metal ceramic based composite, but the challenge is again here because the kind of equipment, the kind of the additive manufacturing machines that we have, they do not support multi-material options. Most of them, like either they are metal or they are non-metals, but like especially the polymers. But mixing metal and ceramic through additive manufacturing is another challenge. So this anyway,
Excuse,
like as we yes.
uh, sir, this experimental facility is available microwave based fabrication at IIT Ropar.
Yeah, like this powder metallurgy, microwave sintering option is there. Yes,
That
not the other
facility.
one. Yeah, yeah, microwave sintering we have in our chemistry department. Like so, we take help from them for sintering a smaller sample.
Okay, and are they using industrial microwave oven there, or
Like no, like see, have uh, the smaller industry, like see, they do not have this, like see, they have high power microwaves which are a mini industrial, this in, like they do not have very big where we can prepare big sample. So what when I'll show, like what we have done, we have prepared a smaller sample because we could, like see, they do not have that kind of facility.
and they are utilizing that microwave spark concept also. Uh,
No,
wi-
no, 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 no. That is separate. This is spark
Spark
plasma
plasma
sintering
sintering,
is,
that is separate, that
we do not.
not from the
Yeah, that
microwave,
is
sir.
separate. No, 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 no. Spark plasma sintering is another technique. So uh, we have got some samples printed from one of our collaborator, but like we do not have that facility.
Okay, sir. Thank you, sir.
Okay. Oh, yeah.
Good evening,
So
sir.
yeah,
Good
good.
evening.
Thank you.
Sorry to interrupt
Yes,
you, sir. Good evening.
yes, yes. No
Sir,
problem. Yes.
I have a question. You are talking about
Mm-hmm.
bioceramics. So, what I
Yes.
wanted is, what is the basic source of bioceramic? Is it plants, animals, bacteria, microbes, or anything else?
These are like see, normally from this biomaterial sources, calcium, some like natural material bioceramic found in animal bones or human bones.
Okay,
So like
okay,
yeah, some of those are kind of used for generating this.
okay, sir. Okay. Thank you, sir. Thank you.
Yes.
Sir,
Yeah.
there is a query in the WebEx chat box, in the meeting chat box,
Mm-hmm.
from Dr. Satvinder Singh. Uh, he is
Okay.
asking, can researchers from other institutes use microwave sintering on paid basis, sir?
Like I'm sure, like the I'll have to check with the chemistry department persons, but yes, like I'm sure because most of the facilities which we have being government institute, that is open to all for yeah, obviously like paid basis, but it is, yeah, open to all. You can write to me this Anupam at IITRPR dot first name Anupam at IITRPR dot AC dot in. I'll check and then let you know.
Yes, sir, that will be a very good option for all the delegates. We have delegates from across India, from Chandigarh, Haryana, Punjab, Himachal Pradesh, Uttar Pradesh, Uttarakhand, West Bengal, Bihar, Jharkhand,
Mm-hmm.
Mizoram, Odisha, Madhya Pradesh, Maharashtra, Andhra
Oh,
Pradesh, Karnataka, Kerala, Tamil Nadu, and Telangana. And I hope
oh.
they will be really
Mm-hmm.
benefited if they can utilize the experimental facility available at your institute.
Most of the facilities are there at the
Sir, there seems to be some network issue. You are not audible, sir.
is it fine? Better now?
Yes, it is better now. Now you are audible.
Okay. Yeah, actually, there was some issue with our institute network. So I have connected my laptop with my mobile hotspot. Some issue was there. So like maybe sometimes if you hear any, like if you have any difficulty in hearing, I can just kind of relocate to some other place so that better signal is there. So
It is
shall I
clearly
continue? It's
audible
okay.
now. Yes, yes, it
Okay,
is
fine.
audible.
So
Please
yeah.
continue.
Okay.
Thank you.
Okay. So yes, like yes, thank you. This presence of bioceramics, as we were saying, not only enhances the mechanical properties, and then it also increases the bioactivity. So that is what is something which the next generation bioimplants want to have. Like there are another class which is polymer based biomaterials, so like a lot of fixation devices and then stent and other being developed. Like so we have not worked on this, so I'll just quickly skip. But like polymers based biomaterials are like this PLA and poly PCL. So like all these are also some options which people utilize for different set of implants and implant based applications. Like one of our colleagues, Dr. Dheeraj Mahajan, he works in the area of developing the polymer stent polymer bioresorb polymer based stent. So so these are another set of biomaterials. Then the other class is polymer and ceramic based. So not just to support but also to take part in the healing process. People do polymer and polymer ceramic. So this is another way just to complete the discussion. But our work is primarily on this metal and ceramic based biomaterial. The final set of slides for introduction. So the issues which normally are faced is like when, since we are focusing on bone based implants, so when there is a interface between like where the bone and the implant meets, bone plant interface, so then there are because of the inherent hardness of the implant, because bones are much softer as compared to the metals, or even like since we are just dealing with the traditional implants, the metal based, so bones are much softer than the metals. And then because of the inherent surface roughness of the implant, there are always some friction, some like degradation of bones that may take place. The implant may like the interface, bone implant interface may contain this some of the like this blood particles, some of the dead tissues, and then some the other crack which may form. Why? Because the issue is that the stress shielding. So I'll go back to this slide. There is a phenomena which is happening known as stress shielding, which does not allow the bones to get strength. Rather, all the load is being taken by the implant itself. So, as we know that bones, they start regenerating itself on its own. So, if somebody sees like a small fracture or hairline fracture or something, even if you do not do anything, after some time, they like the bones will heal. But bones will heal only if they are under load, under stress. If they are not under stress, it will not heal. So, what happens when we have this metal implants? So metal implants, they are higher in strength than the bone itself. So what it does, it takes all the load. Now the bone will start degenerating. Instead of regenerating or healing, it will start degenerating. So that phenomena is known as stress shielding. So it occurs when implants, metal implants, they are used to do the surgery, or they are used to kind of support the bones. So they take all the load, and then they do not allow the bone to grow, which is very dangerous. So what we would need ultimately is that like the bone may degenerate completely, and then maybe a new bone or bone type of like bone kind of material based structure has to be fixed later on. So what we want, that the strength of the implant should be like, what is the remedy, that natural thing that we comes to our mind is that the implant should have strength which is similar to that of the bone, so that even though it supports, it allows the bone also to get its share of load, and it generates, it regenerates, it heals, and then gets the strength eventually. So normally we see that the Young's modulus of most of the materials, like this titanium is almost like 110, stainless steel 190, magnesium is this, polymers are weaker. And when we see what is the Young's modulus of the bones, so like the cortical bones which is outside, so it is about 20 gigapascal. So much less in strength than what the most of the metallic based implants have. Polymers, but we do not want, like, because polymers they are not having enough strength to bear the weight during the cyclic loading especially. So anyway, this is something which we wanted to address. So our target is to have the strength of our finally developed biomaterials, the mechanical properties to be in a lower range than what the traditional metal-based implants have. So, like I said initially, that biocompatibility is something which for which we will have another slide, but I think it's not much required. But because we understood that biocompatibility is the ability of a material to perform with an appropriate host response, or like it should take part in the process of healing, as well as it should not like it should mix homogeneously, or like it should allow the bioactivity to happen, regeneration to happen, and it should not have any toxic effect at the same time. So all these are there in biocompatibility. Like all these are required to be there in in a material to be biocompatible and to be used for anything which has to be inserted in the body. The other thing is about the functionally graded material, because the bone not only has requirement of strength with lower strength, or that kind of strength requirement, but also the gradation. So gradation is something which, as a mechanical engineer, we know that, like, say, high density to low density, high porosity to low porosity is something, that kind of variation. So these functionally graded materials can be of different types. One of that is mechanical material or chemical composition based gradation. The other one could be microstructural, some like depending upon, like, the this fine grains to coarse grains, or porosity gradient. So like either material, okay, like so here it was like material or this combination. So different materials at different sections. Here it is like a different grain structures or microstructures at different sections, and here it is like different porosity at different sections. So it could be anything. The natural bone, they have a combination of this, but like primarily the porosity gradient based. So this material gradation based also, this is possible, like uh, depending upon we can have different materials or combination of the same materials in different porosity. So the method that is normally used for making this kind of thing is by first preparing the powder. So like the powders, they are prepared by it is a schematic, it is showing the centrifugal mix powder method to fabricate the FGM. So like it is in this method, outside will be this more dense as compared to the inside of the material, and so on. Natural bone is like that, and that is why we want to mimic that. Like, I think enough of that introduction. So first I'll play that small video, and then I'll go to the research part of that.
Sir, please increase the volume if possible.
Just disintegrate on its own. If you make it very thin, you can do biodegradable sutures and you can staples. With support from the National Science Foundation, materials engineer Jag Sankar and a team at North Carolina Agricultural and Technical State University are working to make that happen. Here at a center called Revolutionizing Metallic Biomaterials, developing new metals for use in plates, staples, heart stents, and surgical screws, all designed to eventually just dissolve away safely. Which means the future implant, whether it's orthopedic or a cardiovascular, after the person cures, slowly it will biodegrade and it won't be in your body. Sankar says creating new biomaterials from scratch is much easier said than done. You need to have facility things. Materials engineer Christopher Smith says a main ingredient in their biomaterials recipe is magnesium. Our bodies use it to build bone and muscle, and so that makes it an ideal building block for new biodegradable metal alloy implants.
We take a pure magnesium block, we cast it until it becomes liquid molten magnesium. Then we add our additional metals to create our alloys. These elements make our alloy more robust for medical devices.
It's good. Yeah.
Sankar says they're testing a range of different magnesium-based alloys. One type does not fit all.
So that means we need to create a material database, slew of materials having different magnesium alloy property. What suits for me at my age is different from somebody else of some other age or a woman. We are developing a recipe.
Sergei Yarmolenko is formulating biocoatings that are applied to the magnesium alloys, keep them from dissolving too soon.
To develop very tiny and very accurately layers of materials which you want.
Chemist Boyce Collins uses CT scans to monitor implants as they disintegrate.
We can take an image at 2 weeks, 4 weeks, 12 weeks. This is a magnesium anchor that's been absorbed into a rabbit femur, being the thigh bone.
It will take years of testing to make sure these materials are plates off metal detectors at airports. Won't have to be a permanent fixture at all. They'll just disappear on their own. Science Nation, I'm Miles O'Brien.
This kind of shows what or in a nutshell what I was trying to explain is something which is to bio resorbable, and then in order to also take part in the bioactivity, make the bones heal faster, get a strong strength as the implant, and then slowly the implant gets uh, absorbed in the body. So what we could identify from all this is there's a need of a material to we need a material and design of implants in such a way it can reduce the stress shielding effect, one of that, and then bone losses due to this bone implant interface activities. There are several things that happen which degrade the bone at the bone implant interface. There's a need of developing a material, a composite material. Metal ceramic base is something which is attempted and then should have the functionally graded properties to mimic the natural bone. And then some of the techniques like fabrication routes, so either powder metallurgy based or for complex geometry, this additive manufacturing based, and so on. So the titanium, the selected materials were titanium and hydroxyapatite. So the titanium is non-toxic, so it has no natural role in human body. So this one thing which is good about titanium is its good strength to weight ratio and then non-toxicity. It does not take part in any of the this activity inside the body. So that means in a way it is good, but in order to do what we want, we have made this mixed hydroxyapatite, which is an integral part of human bone, and it provides hardness and toughness to the natural bones. Now if we try mixing it in different ratios and then see if we can get the properties as we desire. So different materials, they were mixed using this mechanical alloying, this ball milling kind of process. So several attempts were made, several number of hours that we tried, and what we found that at some of these parameters yield some speed of ball milling, ball powder ratio, ball parameters, and then some 4 hours duration, etc. So some after several trials and error, we could find some ideal parameters for this ball milling process parameters, and then we tried to identify whether the mechanically alloyed metal ceramic powder, it has all like the correct ingredients of titanium hydroxyapatite. So we performed this XRD, this X-ray diffraction test to study the existing phases and then the crystallinity of the titanium hydroxyapatite mill powders. Then we also perform this FTIR to identify what kind of organic and polymeric and this inorganic material, along with its quantitative and qualitative analysis of like different groups, reactive groups, hydroxy, like OH group, this PO or like the PO4 groups. So like in pure titanium, 1%, 2%, 3%, 4%. So like in different percentage of like in different ratios, we mix hydroxyapatite in the parent metal powder, that is titanium, and then we wanted to see like what is an ideal percentage and what percentage we should mix. So we tried with several initially we tried with several percentage, like we kept the hydroxyapatite percentage low because what we found like in at a later stage that as we keep on increasing hydroxyapatite percentage higher, it becomes difficult for us to retain some of the functions. I'll show that. So then we also perform the SEM analysis, and then the composition, as I said, we varied from pure titanium to titanium 4%. And we one of the key things that we want is something like this calcium to phosphorus ratio should ideally be in the range of like 1.4 or so. So like for 2% HAP, it was 1.42. For all other percentages was slightly higher than that. The compaction, like the what we found that okay, like for all of these anyway, we'll try compacting them and we try to make this sintered sample. So we took this material, and then we do, did this compacting and pressing, and then we did the microwave sintering, and then we fabricated the sintered material, sintered sample of pure titanium, different percentage. So like here we have shown this titanium 3% HAP. So these white spots, they show the presence of this HAP. So like HAP was found to be decently homogenized, like not ideally, but like decently homogenized. We also tried and see what is the hardness value of that for different samples. So this, and then the modulus which is there. So modulus, if you see the modulus of this hardness and modulus. So this modulus is shown by the black color curve. So for pure titanium, it is very high, and for titanium mixed with hydroxyapatite 4%, it is as low as about 50 GPa. And if you remember, the cortical bone was about 20 GPa. So like we are coming closer to the strength of the bone. However, at 4% we face some issues, and like 2 and 3% were quite ideal, where like the strength is about one third of what the commercially pure titanium has. The hardness is also reduced, so the metal or the like not and bone interface can now take a breather. It can uh, like it will not go that kind of degradation along the interface as it used to go undergo during the metal only kind of implant. We also try to do like to in order to verify what kind of tribological conditions it has. So a scratch test for different values of like different ratios of titanium and titanium hydroxyapatite. So we found that like it is almost as good as commercially pure titanium, barring 2% HAP for some reason, where the coefficient of friction was quite high, maybe due to some error in our mixing of like of that sample maybe. So like we analyzed the scratch test track, wear track, and then uh, along this scratch test we found like we also saw what is like is the hydroxyapatite getting this sedimented at some places, like higher percentage of hydroxyapatite, we found that it is easily getting disintegrated. For 1 to 3% it was decently okay, like especially for 2%, but higher percentage was not preferred. So that's why like we did not prepare very high percentage of hydroxyapatite later on. We also did like in order to find out these elements and other things, ADS mapping along this batch test to see what kind of elemental composition it has. We also performed this wettability test. So what ideally we want that like the implant should be a kind of hydrophobic in nature. So like it should not have this kind of thing, some like contact angle. If you see, it keeps on increasing, but still it is not hydrophobic. It is kind of like the in this range of less than 90 in all the cases of like hydrophilic. So see, one way it is okay for us, like we were fine that okay, if the titanium it is not taking any part in the uh, or like it's non-toxic, it's not doing anything to it, either the bodily fluid or anything. So even if some bodily fluids are coming and then they are getting into the pores and then reacting with hydroxyapatite, they may actually increase the bioactivity. So we found that even though it is in this range and then it is hydrophilic, it's fine, like we were okay with that. So we thought that okay, let's try making some sample, not just like of solid sample or like equal density sample, some varying density sample also we should prepare. So like this mixing, alloying, and then stacking in different this so like starting with 100% titanium at from one end to 95% titanium and 5% at HJP. So that kind of variation. So we stack the different layers with different composition and then press and then compact it and then centered it to make this sample. Now fabrication of this FGM was a challenge. See, simpler solid like or equally porous materials were easier to do it with centering. However, this was really a challenge. It was not very well prepared a sample. We wanted so like the next thing that we are trying is to do this kind of gradation using the SLM process, the selective laser melting based process, so metal based additive manufacturing process, for which we have this SLM based EOS M290 this LPBF or SLM based machine which we have. So what we are trying now is that we pre-mix some powder at the pre-mix the powder of titanium with hydroxyapatite in different percentage and keep it ready for layer by layer fusion. Like we are so far successful in making only one single percentage of titanium and hydroxyapatite mix, but our target is to vary the percentage as we grow. This powder fusion based processes, they are quite good in achieving this kind of thing, but multi-material is a challenge. This like there are range of powder bed based processes and processes which we could try, like slightly inexpensive or like easier techniques start from selective laser sintering to more advanced like selective laser melting, and in some cases like this electron beam melting also can be used. uh, like I am not going much into the details of each of these processes because like then we'll turn our discussion into a different direction. But this selective laser based melting based system, they are good because uh, different materials, when we try to mix like different class of materials, metal and ceramic. Hello, hello, is there any question? It's okay. So yes, like as I was saying that like there are challenges when we mix multi-materials in SLM based thing, because normally there's a single feeder through which the material or powder is supplied. There are like details about how selective laser melting works and other things, but one of the key things is about this SLM based processes. If we want to make that kind of thing, is that like it is suitable for metal and ceramic material both. So that is one good part. So it's not just for metals or ceramics alone. So this is good metal technique. For SLM technique is good for metal and ceramic both material. Material wastages is also less, and then it is easy to fabricate complex shape parts. Like this goes without saying for any of the additive manufacturing processes, but particularly very relevant for our thing, because any kind of implant that we want to make, it has by default a very complex shape. So this is something which is required, and which it makes this process a good candidate for making the uh, implants based on the newer biomaterial. However, yes, there are definitely several limitations and other issues, like presence of residual stresses because of very high heating and cooling rates, which is a challenge. Then sometimes unwanted porosity. See, we want planned porosities wherever we want design porosities, but because of the inherent nature of the way the process, like the way the bonding takes place during this process, there are unwanted porosities also sometimes. So there are distortions because of residual stresses, induced porosities, shrinkages, and other things, which can be tackled based upon the process parameter optimization for a given set of material. Like so, like before we could we started making this use of the experimental facilities. I'll show one maybe first. I'll come to that. Now what we have is a this laser based SLM metal 3D printer with 400-watt laser. It can make use of most of the metal and metal alloys uh, and mixture of metal and ceramics that we have tried. So it has been able to melt it to the required temperature and then bond it to make useful products. Recently, we have made a very complex part, a turbine part, for using this machine based upon this aluminum, magnesium, and silicon based alloy material. So like this kind of facility we have used. So but see, because even using that facility is not cheaper. So like what we wanted to do is that, like, see, before we jump into the costlier part of experimentation, we should kind of learn some of the basics, or like some of the we understand what kind of parameters we should select. So we did like a range of these things. Like we started with some analytical formulations, like some finite element and finite volume method based analysis to find out what kind of process parameters we should select. And then we also tried doing this multi-scale modeling approach on COMSOL, where we simulated what is the key thing here is this moving part that is known as melt pool. So we to know that what is the correct characteristic that we should get here, so that what we finally get out of experiment is the desired part with correct like almost no distortion, the desired porosity, and then well mixture of the biomaterial. So like there were a set of output decision making parameters that were there, and then one of that was the melt pool, its shape and size, melt pool dynamics, the stability of the melt pool. So like this area, like where the laser interacts with the metal or metal ceramic based powder, is the key to determine everything. Melt pool is like we have in our body genes. So like the genes, they define the entire thing. So like melt pool, they determine, or they control the entire part property. If we can control this properly, we can control the part properties very precisely. So this melt pool mode of fusion, the key parameters, they are energy density, like how, what is the hatch, like the laser spot diameter, the velocity at which it should move, the hatch spacing, the spacing between two consecutive tracks. So there are like so many things to determine before, like one domain is by preparation of biomaterial, which we have seen, like, which is quite complex. Once we have made
Sir,
that,
good evening.
how do we
Sir, good
determine?
evening. Sorry to
Yeah.
interrupt you, sir. You
No,
were
no
you
problem.
were talking about simulation. Is it MDS, molecular dynamic simulation studies?
No. So like what we did was so far is there are two things that we did. One is analytical formulation we did.
Okay, sir.
The other thing that we did is finite element based simulation on COMSOL. So using this macro and some part of meso scale. So like this micro scale atomic thing we are not done completely. Our lab is doing that, but we have not been we are not able to get to the final results yet. We are
Okay.
trying this using our another software, this dynamic based software as well. But yes, like so far the results are based on this analytical and finite element.
Okay, thank you, sir. Thank you.
Yeah, like, but very good thing, like, because the if we have to, like, very good question, because if we want to get the correct this properties or correct output, we eventually have to go to micro scale, the atomic level, because here the interaction of laser is to a spot diameter of few tenths of microns. So like only few thousands or like few hundreds to few thousands of molecules they take part at a time. So like that kind of simulation is ideal, but like even our finite element based method, like this model, they to complete dynamics based simulation will take even longer. Like what we are trying is that a combination
You
of
are not
something to
audible.
optimize that. Shall I move to
You are not audible, sir.
let me try again?
Yes, now it seems better.
Huh? Yes, is it
It's
better?
yes, sir.
Yes,
Yes, sir.
now
It's okay, sir.
you are audible
Hmm.
now.
Okay, yeah, fine. Actually, I think I just relocated my mobile phone to some other place. Okay, so yes, like a lot of things, like as I said, like there are two different domains now. Development of biomaterial based this different biomaterials, powders of that, and then one way easy was, or like relatively easy was, to directly center it to kind of like without much of gradation or in a simpler geometry. The other one is to determine several set of parameters and to understand the effect of these parameters on the final part properties by analyzing through different means the formation of melt pool in LPBF, that laser powder bed fusion based processes, the SLM process, for example, here. So yeah. Mm, just a moment, I'm trying to go to the next slide. Yes. So uh, correctly asked by one of the participant, that modeling of LPBF. So modeling of LPBF from a simpler approach to it is going up to the molecular and atomic level, phase field modeling, and then we can even try modeling different regions of the part, either like say in multi-scale, like like molecular based model here, and then rest of the places it could be just a continuous like finite element model and so on. So like there are several researchers working on improving the modeling accuracy of the this thing. So like we tried in our simpler domain. So like this is kind of a filler slide which says that by doing all this we are being a manufacturing and we always try to whether we are trying to like we can somehow help in developing like or making our product industry 4.0 complied or not. Some like additive manufacturing, simulation, they both are anyway pillars of this industry 4.0. And then nowadays like different AI tools and other things, so like people may use some of these tools to improve the prediction accuracy as well. So we tried implementing some of these AI ML based model also, because every time it is not possible to do the analysis or the finite element analysis to get all to the results. So like we tried developing some data set and then use AI ML model also to use the like instead of directly simulating it, we use AI ML model to predict the input parameters for some of the biomaterials. So some of these approaches, so like this slide we anyway had seen earlier, and all this like something which I would like little bit skip and go to a little later part. This barring this slide, so like this slide I'll explain in some detail. Like as I was saying this SLM is the key, the gene, the key characteristic. So melt pool looks something like this if we see this microscopically. So there are like key characteristics of like when a part building process is going on, it will the melt pool will reach a steady state. The length, the width and the depth of the melt pool will almost stabilize to a constant values which we want should be the ideal values will improve distortion, will reduce distortion, it will reduce the unwanted porosity, it will remove the undesired residual stresses, it will uh, improve the ductility, and then it will also not let it cause the balling effect. There is a typical defect which is balling defect in most of the SLM based or LPBF based processes. And the process parameters which determine or which control this, they are laser power, scanning velocity, spot diameter and layer thickness. So a set of modeling, first level modeling, second level modeling was done in order to predict the melt pool dimensions for a given set of variables and then optimize it. So then this in a nutshell is something which we attempted before choose to decide what kind of the input these parameters we should have for the 3D printing using SLM for our biomaterials chosen. So like I'll just skip. There are several other phenomena which happens, which we have taken into account while we have developed the analytical and the other model. Like okay, this I'm just skipping. However, when we are making this FGM functionally graded material using the SLM process, there are several uh, even though we are able to process one layer at a time, even though we are able to engineer the material properties within the layer itself, the challenge is to find the correct like say, because like if the the metal and ceramic they are mixed together, we cannot like still date we do not have the kind of facility which can vary the laser density at every point. So ideally we should be able to vary the laser intensity, not density, intensity at every point within the layer if we want to fabricate that very nicely. Now using SLM process with the existing method, only one directional gradation, like say we can have some gradation in the structure maybe, but having multi-directional gradient, or we being able to process correctly with the correct set of parameters, like say we can predict that okay, for each point in the material we should have the laser intensity some specified value, but having that facility available in the machine is something which is not yet there. So there are challenges like using analysis and using the technique, simulation technique, we are able to find what is the ideal parameter, but we are not able to give those parameters using the machines that we have. So this kind of facilities are something which are very much required. So what we expect that with the development of the 3D printing technology, these functionally graded scaffolds can be fabricated to support all these damaged bones, and then the mechanical and biological properties can be improved. The uh, thing that Another thing that we have tried is that like the is one is based upon the different materials as we have tried. The other thing is based upon the structural variation. So this bone the bone micro CT results literature, it reveals that it has a porous this kind of structure which can be mimicked through some of the mathematically defined structures. One of that is triply minimal surfaces based structure. So not just by varying the material composition, we can, with using the same material composition, vary the porosity and strength by varying the kind of it has from outward solid to inward porous, using some of these mathematically defined structures. So like uh, one of my student, he worked on developing this gyroid based scaffold using this. So like he has printed it using the polymer, like this is something which is based upon a polymer material based, and then from outside solid to inside porous, using the triply periodic minimal surfaces, which is gyroid in this case. And then we performed some of the uh, just where it is, yes, we performed some of the tests, compressive behavior. This okay, this figure is not there. So compressive behavior, and then we found that these perform decently well uh, for scaffold-based applications. And since they have this porosity, they will like if it is made from the correct biomaterial, it will also allow for the bioactivity to. So like different images and other things of that. Now, since we have talked about the biocompatibility a lot, so the biomaterial that we had developed, we conducted a cytocompatibility test on that. So, in order to check whether it allows for any bioactivity or not. So, this cytocompatibility in that test, the sample is kept in a liquid medium, which is known as simulated body fluid, for a number of days. So, like for like I think 7 days we had kept. So, what like we found that the scaffold will be like the target is that scaffold gradation will be set to predict density measurement. So, to graph is there, like so that uh, we this environment, there was some growth so observed. So like that kind of put given an evidence that we were able to uh, like developed biomaterial was able to allow the growth of the cell in uh, uh, in the simulated environment. So, like to summarize this, what we tried, and then in the future is something where biomaterial group characteristics that are needed to be explored in the limits of existing biomaterial combination of biotherapeutic or polymer and possibly solve issues this activity and mechanical property. So like the other thing that stress shielding also like the data I did not present here, but we were able to, as like you could remember, the Young's modulus were quite closer to the natural bone. So like we were kind of able to take care of the stress shielding, but we have to improve on this between implant and the existing bones. Biomimicking application, bio structures just like TPMS based structures, they have a lot of potential, and it needs to be explored carefully for designing of bioimplant. The material and design aspect for biomedical devices, they needs to be explored to fabricate better and efficient implants, and development of different AM based processes and improvement of the existing AM processes in order to suit the requirement or customization of implant fabrication to improve the market capital of the manufacturing of these biomedical devices. That is very much uh, required. Yeah, thank you so much for your patience. I'm open for questions.
Thank you, Professor Anu. Very informative presentation given by you, sir. And there is a new study which we have learned many things from
Thank
this
you.
presentation. So, any questions from the participants, please?
Yeah, good evening, Dr. Anupam.
Yeah, good evening. Hello. Hello. I'm not able to hear the question.
Hello, hello. Am I audible, sir?
Yes, yes, you are audible now.
Yeah, sir, I am a dentist by profession, so we do work on dental implants very often. So, looking at the work on implants, because titanium is the main material, what we in today's, I'm saying contemporary time, titanium is the prime material used for dental implants. So, what I wanted to ask you is when we are utilizing a component like hydroxyapatite into it, though they are both material are melted and they are printed together. So since we are looking at the stress shielding, probably that is a behavior at the interface of the implant. So we commercially there are coated implants which are available. Coated means they have a layer of hydroxyapatite at the outermost part, but the core remains the titanium. So, will the performance in terms of physical features or compressive strength or tensile strength, will the performance of the implant vary if we have a material which is 3D printed, like a complete composite of two materials? And the
Yeah.
other one having a titanium core and a coated HA, which is basically a thing required at the surface. This actually came to my mind because of course there's a lot of intensive work going into uh, a production of a completely composite material. So that is why I'm curious to know, in terms of physical performance, in terms of cost, how it shall how it shall perform vis-a-vis a coated implant which has a titanium core but HA coating.
Okay. Yeah. Thank you, Dr. Vishaka. It was like very relevant question. And then the like the when we think about the dental implants, so there like the application is such that, as you rightly said, like the core is metal, that is titanium, and outside of that is coated with a ceramic like zirconium or some other similar
Even
the
also, sir,
ceramic material.
hydroxyapatite also, because
Okay,
that is,
hydroxyapatite.
yeah.
Okay. Yeah, so like see, there since outside of the like the this outer thing, like inside the core titanium, it provides strength there, and then outside of that is in touch with the whatever, like the food or tissues and other things.
Yeah.
So and then
Hello.
I think that kind of it will of this hydroxyapatite and titanium in order to let the cells grow all across that, whereas the requirement in case of dental implants is that to provide strength from inside,
Mm,
and then to have this kind of like no reactivity, or like at least like biocompatibility from outside.
mm.
So probably that is where like strength wise, if we say strength wise, the homogeneous mixture will probably have better strength
Okay.
here. Yeah, here what will be different is that like if the let's say dental implant will come under much of load,
Mm,
the outer layer may start cracking.
okay.
Yeah, like sometimes like even I have my personal experience like this. I got like three of my teeth this using some this implant metal and then ceramic implant.
Mm,
So outer layer, one of the this implant got chipped off
mm.
little bit
Yeah,
when under
is
load.
that is a problem because the outer material does not have that kind of
Yes,
mechanical strength as compared to titanium, and there is a likely, I'm say, high chance of fracture
chipping
or
or
micro cracking or chipping and stuff.
yes, yes, yes. So that would like so like here it is okay because like it is not taking load all the time. So it is okay. Like it is a good solution. But
And
ideally it should be a good mixture, homogeneous mixture.
okay, would that be more costly if it comes to market? I'm saying, will it be costlier than the other one?
Yes, because like it involves one additional step of this. Like the coating is like that also will be some, like the coating again is a process, but coating is kind of like which we have reached to a level. I think I'm sure the participant will hear from Professor Harpreet Singh about coating tomorrow. But like coating has reached a level where we have kind of commercialized and made it more cost effective, whereas
Okay,
making this homogeneous mixture and then printing or making fabricating the parts using that is still kind of in under developing stage.
involves. Right, right.
Yes.
Interesting work, sir. Interesting work and wonderful presentation. Good to hear from you. Thank you. Thank you, sir.
There's some, yeah, yeah. So other questions, if
So,
any?
so any questions from the participant? Okay.
Hello.
So I
Yeah.
have one question. Yes,
Mm-hmm.
you have prepared a slide in which the SLM is used to make a structure which has been mixed of titanium and hair powder.
Mm-hmm.
So, so how this titanium metallic powder is diffuses in HAP ceramic to make a good structure? Because
Yeah, actually correct. Like this, what like because of this only like we mixed only like 2 or 3 or maximum 4% of hydroxyapatite, because fusion of these particles were very challenging. So like sometimes what happened like during initial trials, hydroxyapatite started burning at the temperature where the processing of titanium will start. So we kept the parameters to a very lower value, and then the kind of bonding that was achieved was not completely fused. Like there were not very strong bonding that we could achieve. So ideally, as I was saying, that we wanted that titanium to be processed at a higher laser parameters, and then wherever the hydroxyapatite is there, the laser parameter should be at a lower value. but we were not able to achieve correctly that.
Okay. Yes.
Yeah.
This is the point of research, actually.
Yes, yes, yes. Become like that kind of machine or capability of the machine should be there, which can process
Yeah.
one point at a time.
And the temperature will also change the structure of titanium
Yes,
particle, I
yes,
think.
very correct, very correct.
So,
Yeah.
any questions from the participant, please? So, I think you have addressed all the questions to
Yeah.
the participant very well, sir. And your presentation is very clear, and we understood each and every point explained by you. And this definitely help our participant to extend their research in the area of biomaterials, sir. So,
Yeah,
thank you,
definitely.
sir.
And then like yeah, I'll be like kind of happy if I receive some emails and then some queries, and then definitely like if this microwave centering thing, if some like few researchers would want to use that facility, I can find the source and then what kind of charges and other things are there. They can write to me.
Yes, yes. And this was the one of the question by our participant. Uh, Thank you, sir. Your support is very kind to us. And I will share your email with the participant if
Yes,
someone
yes,
will.
yes, yes. Yeah, definitely.
Yes. So, that's the end of today's session.
Thank
So
you so
I
much.
can, so I can say goodbye to all my participants. Thanks to all the participants for their patience. Thank you from my side. Thank you, sir.
Thank you. Have a good night. Yes.
Mm, thanks, sir.
Yeah, I'll disconnect now.
Yeah, sure.
Yeah,
Please.
thank you everyone. Thank you to the organizers and to the participants. Yeah,
Uh,
bye bye.
Our pleasure, sir.